Hello, Pre-AP Chemistry. In this podcast, we're going to go over how to use equilibrium constants to solve problems where we're given an equilibrium constant and a chemical reaction, and we need to find out the concentrations of everything in the reaction at equilibrium. So we're essentially working the problems backwards from what we were doing before. To do this, we're going to need to use a graphic organizer. And that graphic organizer is called a Rice table. In a Rice table, you'll notice that the RICE in this acronym are all capitalized, meaning that these all stand for something. So those letters mean R stands for reaction, I stands for initial, and those initial concentrations. So the molarity that we're initially given of each thing in the reaction. The C stands for change, so we either gain some or lose some of each species in the reaction. And finally, E stands for the equilibrium concentrations. And the equilibrium concentrations are the most important part because those are how we calculate our equilibrium constant. So, the way that we can really get good at using Rice tables is to work some examples. So let's look at one of those examples. So I'm going to write a very general reaction. A becomes B. Both of these are aqueous, so there's nothing that I can throw out of this reaction. And our K value is very small, 1.01 times 10 to the minus 4. So mathematically, we would have 0.000101. So this is a very small K value, showing that the reaction's happy place is going to be very far on the left. We would look at this reaction. If we were to see this reaction going on, we might even look at it and say the reaction's barely even happening. And that K value shows that this reaction truly is barely even occurring. So, is this reaction product favored or reactant favored? The low K value indicates that it is very highly reactant favored, meaning that it will barely even occur. The left side, our reactants, our starting materials, are going to be in much, much higher concentration in the end than they are in the beginning. However, as chemists, we need to know this objectively. We need to find the exact concentrations of everything at the end to prove this. So that is what we need to do in this problem. So if we start initially, and that's what the word initial means, our starting materials. If we start with 0.05 molar, and that's what the big M stands for, is molar, moles per liter. If we start with 0.05 molar A, so our reactant A, and that's in its aqueous form, so dissolved in water, what will be the concentrations of each substance at equilibrium? So I'm going to start this problem by making a Rice table. And a Rice table is very simple to make. I'll take RICE written down the side of my paper. R stands for reaction, so I'm going to write my balanced chemical equation on this line. And that's very simple to do, especially with this very generic reaction. A in equilibrium with B. Now, I'll put over here the K value just so I have it to look at when it becomes relevant. 1.01 times 10 to the minus 4. Okay? I stands for initial conditions. So we're given the fact that we start with 0.05 molar, and we have to put molarities into this. 0.05 molar A. So I'll put 0.05 molar. It's not necessary to include the units in your table. They just tend to take up space, and I don't know about you guys, but I find them confusing, so I will leave the units out. So I'll just keep in mind that this is molarity. And if it doesn't say that anything else is in the flask, assume that nothing else is in the flask. So therefore, our amount of product, since the reaction has not begun yet, will be 0. So our amount of B will start at 0 unless otherwise specified, which they did not specify. So those are my initial conditions, 0.5 molar A and 0 molar B. Now the change. I don't have any B to start with, but I do have some A to start with. Think of our reactants like gasoline and air with a car. Those are the things that make the engine run. As the engine runs, I run out of gasoline. So as the engine runs, as this reaction proceeds, I'm going to lose some of my reactants and I'm going to gain some of my products. But I don't know how much. So I'll use the variable x. So I'll lose some reactant. And since I have a 1-to-1 mole ratio between A and B, I'm going to gain as much B as I lose of A. So I'm going to have minus x of B, and I'll have plus x of B. So I'm sorry, minus x of A and plus x of B. So my equilibrium conditions, I'm just going to take these numbers and combine them. So 0.05 minus x, and 0 plus x is nothing more than x. Now this equilibrium section is going to be the important part with what we do next, because we have a k value, which comes from a k expression, and our k expression is our products over our reactants. So our product is the concentration of B over the concentration of A, which I now have values that I can plug into these. They're not pretty, but they are things that I can plug in. So the concentration of B at equilibrium is right here in my Rice table, is x. And the concentration of A at equilibrium is 0.05 minus x. Okay? Now, since I have an equilibrium value, I can take this expression that I just wrote and set it equal to the equilibrium constant. So I'm going to start down here so I have more room. 1.01 times 10 to the minus 4 is equal to this equilibrium expression, x over 0.05 minus x. Now is where the chemistry ends and the algebra work begins. So, to simplify this and solve for x, I'm going to take this quantity and I'm going to multiply both sides by it, so that way it's out of the denominator on this side. So I have 1.01 times 10 to the minus 4 times the quantity 0.05 minus x. And that will be equal to x. So now I have some algebra work to do to clean up and move x over to one side so I can isolate, solve for x, and plug back into my Rice table so I can find those concentrations. So what I'm going to do now is I'm going to take just some basic algebra. 1.01 times 10 to the minus 4, I'm going to distribute across this quantity. So 1.01 times 10 to the minus 4 that E, remember, translates to times 10 to the minus 4 times 0.05, and we have 5.05 times 10 to the minus 6. And then minus 1.04 times 10 to the minus 4 times x. And that is all equal to x. So I'm getting closer to solving for my x value. Now all I need to do is combine like terms, and I can start cleaning this up. So since I'm subtracting 1.04 times 10 to the minus 4 x, I can move it to this side by adding it to both sides. And remember, when I have just x here, that's really saying 1x. Kind of remember from Algebra 1. I know it's been a while, but that's okay. We're going to stretch muscles that haven't been stretched in a long time. So 1.04 times 10 to the minus 4x plus 1x. So I can take 5.05 times 10 to the minus 6 equals, and then I can just, if this is much easier to do if you translate into the standard notation, 0.000104. So if I take 0.000104 plus 1, I end up with 1.000104x. So I took this, translated it to standard notation, added it to this side, and I now have x. And this is all just me combining like terms and doing Algebra 1 work. So now I'll take the coefficient on this x, divide both sides by it to isolate x. So x will be our 5.06 times 10 to the minus 6 divided by 1.000101. I end up with 5.05 times 10 to the minus 6, which you'll notice is awfully close to this right here. We may notice that taking this portion right here was basically useless. And as chemists, we like to be nice and efficient. So I'm going to show you a step in the next example where we can decide, do we even need to go through this? However, if it becomes confusing to you, just do it and go through the steps as usual. So x equals 5.05 times 10 to the minus 6th. Now we're almost done, because the question said, what are the equilibrium concentrations of A and B? So we're going to take the concentration of A, and we're going to take the concentration of B. Now we'll look up at our Rice table. Our x value is 5.05 times 10 to the minus 6. Our B concentration is simply x. So if x equals the concentration of B, B equals 5.05 times 10 to the minus 6th, and I need to put a unit on there, and molarity, the concentration, which is these brackets, is molar. Now A concentration, I'm going to look up here. The Rice table shows us that we have 0.05 minus x. So 0.05 minus our x value gives us 0.04999. So if we look at our initial values, our initial value of A was 0.05. It barely changed. But as a chemist, we have to be able to go through and objectively decide, did it really change? And to some degree, it did. To some tiny degree, it did. But qualitatively, if we see that our K value is very small, then we know that it's not going to proceed to any significant amount anyway. When we calculate these equilibrium values, it just is to prove that this K truly does mean what we said it meant. Now, a second example, I'm going to show you how we can speed this process up a little bit. So we start with our chemical equation, N2O4 yields, in equilibrium, NO2. So I'm going to start by putting our Rice table together, R-I-C-E. And the R, remember, means our reaction. N2O4 yields in equilibrium, NO2. And quickly balance it, that's a 2. So the K for this reaction, again, is very small. So the K value for this reaction is 2.2 times 10 to the minus 4. Now, as chemists, we can look at this and say this reaction is not going to go significantly to the right. And since it's not going to go significantly to the right, a vast majority of our substances are going to be on the reactant side. So this is going to be in a much higher concentration than this is. But we have to objectively decide that. So we just said that it's going to be a reactant favored reaction, but let's go ahead and prove that. Now if we start, and in this case we aren't given molarities, we're given moles and we're given liters, but at this point that is a very easy conversion to do. Initial concentration, we're going to start with N2O4, and according to the problem, we do not start with any NO2. We don't start with any nitrogen dioxide. It's simply going to be the N2O4. So we're going to take our moles of N2O4 and divide by our liters of gas. So we're going to take our moles, which is 1.1, and we're going to divide by the liters, which is 0.25, and we'll get 4.4 molar for the N2O4. So 4.4 molar. So this is the shortcut that I was talking about. The 1% rule is we can ignore the minus x term if we have a very, very small, and in this case we do, equilibrium constant. And when we start going through the math, I'll show you exactly where that minus x term rears its ugly head. So the change. We know that we have reactants in the vessel to begin with, and what we'll do is we're going to lose some of this, and we know we're going to gain some of this. But if we look carefully at how this reaction progresses, for every 1 mole of this that I break down, I get 2 moles of this. So if I lose x of this, I'm going to gain 2x of this. And that's because this is a 1 to 2 mole ratio. So if I lose 1 mole of this, I'll gain 2 moles of that, hence the 2x. So it's weird to think of, and if I lose some of this, I can gain twice as much of this, but it becomes that because of the product. And literally, this is me taking this molecule and just cracking it in half. So for every 1 of these I have, I crack into 2 of those, which means our equilibrium values is 4.4 minus x, and then 0 plus 2x is 2x. So what I'll do now is I'm going to write out a K expression. And a K expression, remember, is no math. So K expression is our products, so the concentration of NO2. And remember, I write the stoichiometric coefficient as an exponent, so it's NO2 squared. And I'm going to divide that by our reactant, which is our N2O4. So the concentration of the NO2 squared divided by the concentration of the N2O4 just to its first power. Now I'll plug in the equilibrium values that I have written here, and I'll come down here so I have more room. So the K value is 2.2 times 10 to the minus 4. And that equals our NO2 value, which is 2x. But I do have to square it. So 2x, and that is all in parentheses, and then a square goes outside the parentheses, divided by the equilibrium value for the for the N2O4, which is 4.4 minus x. Now here is where this 1% rule comes in. And it looks like a lot of words, but really this will make your lives a lot simpler. If I take this expression and distribute it across this quantity. So if I take 2.2 times 10 to the minus 4, multiply it across this and this, I'll end up with something that looks like this. 2.2 times 10 to the minus 4 times 4.4 Sorry, my phone rang and I couldn't figure out how to turn it off because I'm old. I have 9.68 times 10 to the minus 4. And I will subtract from that 2.2 times 10 to the minus 4. So 0.00022x. So really, if I subtract this quantity from anything, so the minus x term, if I subtract this quantity from literally anything, will it affect a large change? And being such a small number, since it has our variable in it, if I subtracted this from x, so 1x minus this, would it affect a large change? The answer to that is no. So what I can do is ignore the minus x term altogether. So I'm going to take this, I'm going to scribble it all out, and I'm going to get rid of this minus x term. If the k value is small, you can do that. Okay? And this is a small k. Since this is a small k value, I can ignore this minus x term because it will not affect a large change. So I'm going to go on without this minus x term, and you can do that if this k value is small. If this k value is small, you can ignore this minus x term. You can even ignore it up to here. So, but if that's confusing for you, you can go ahead and leave it in. However, I would not recommend that because then you'd have to do a quadratic equation, but we'll leave that to the next. We'll leave that for the next step. So I'll take this 4.4, distribute it across. So I have my 9.68 times 10 to the minus 4, as we had in our last step. 2.2 times 10 to the minus 4 times 4.4 gets me that. And that is going to be equal to 2x quantity squared. Now, when a square is outside of the parentheses, just a real quick algebra review, we square everything inside the parentheses, including the 2 and the x. So 2 squared is 4, and x to the second power is x squared. So our equation got a lot simpler by ignoring this minus x term, and we can do that again if the k value is a small number. So to get rid of this 4x squared, I'm going to first divide by 4. So 9.68 times 10 to the minus 4 divided by 4 gets me 2.42 times 10 to the minus 4. I'm not quite done yet, so that's x squared. So the square root will give me my x value. Is 0.016. Now, to find my equilibrium concentrations, which is what we're trying to find, the equilibrium concentration of the N2O4 and the equilibrium concentration of the NO2. I'm going to look back up at my Rice table, 4.4 minus x. So 4.4 minus 0.016 will give us 4.38 for our equilibrium concentration of N2O4. And that's molar because we're talking concentrations. And NO2, we're going to take 2 times x. So I have 0.032 molar. And using Rice tables is really not that big of a deal. They make our lives a lot easier. Just remember reaction, initial, change, and equilibrium. Now, if we were to keep this minus x term in, this would turn into a quadratic equation, and we'd have to use the quadratic formula. However, I am not going to do that to you. They don't do that to you in AP chemistry, so I did that to my students today just to mess with them and scare them. So you're welcome for that. And this is the example where you have to use the quadratic equation to find the answer. If you want to work it, This is the problem right here. You can pause the video and you can chew on that for a little while. But since I'm not going to do that to you, that's where I'm going to wrap this one up. So if you have any questions, please let me know. Thank you.